Welcome to the course on advanced machining process. Uh, Last week we have discussed about this mechanism of ultrasonic machining process and different parametric study of ultrasonic machining process. Today I shall continue again this ultrasonic machining process and few applications of ultrasonic machining process and few modification and hybrid machining process by using ultrasonic machining. As I told that it was ultrasonic machining process was discovered by Balamut in the year of 1945. During ultrasonic grinding of abrasive powders, industrial application begins in 1950 when new machine tools appeared. Okay, so we have discussed that there are two types of magnetic type transducers are there. One is magnetic type, another one is the piezoelectric type. Okay, two transducers are there. So in magnetic type transducer, the coefficient of magnetic elongation, when you keep some ferromagnetic material under a varying magnetic field, there is a change in length. So this change in length is del L, and total length of this magnetic coil is L. Okay, so then this coefficient of magnetic elongation is del L by L. So it was discovered by Joule at Manchester 1878. Now, using ultrasonic machining, there are few applications are to cut shallow cavities in hard and brittle materials having a surface area less than 1000 millimeters square. So there are another applications, drilling and coring operation. So this drilling and coring operation can be done using a rotary type ultrasonic machining process. In normal ultrasonic machining, this tool is vibrating at a high frequency in ultrasonic frequency, but in rotary ultrasonic machining process, this tool rotates as well as it vibrates. So in rotary ultrasonic machining process, we are giving some modification to this tool, so it rotates during vibration also. Okay. So a drill bit is rotated against the workpiece similar to the conventional drilling operation. So used for machining non-metallic materials such as glass, aluminum, ceramic, phyllite, quartz, zirconium oxide, ruby sapphire, beryllium oxide, and some composite materials. So you can see here, this is the tool here in normal, it is in the normal coring operation, and this one is the ultrasonic vibration, we are doing the drilling operation. This coring operation you can see that, so this kind of tool is used. Okay, so this is the hollow tool here. And in this case, actually, this much material is not removed. So only this material and this material is removed. Okay, so by rotating this tool, so using this very annulus region, actually, this machining is going on by these two annulus region. But in drilling operation, total volume of material is removed. Okay, so this is the difference between coring operation and drilling operation. In both the cases, this tool is actually rotated. So it is rotational ultrasonic machining process. Okay, so these advantages are there due to this rotation high removal rates. So your removal rate increases. In normal case, there is no rotation, but in this case, because of this rotation, so we can expect more material removal rate in case of rotary ultrasonic machining process. So lower tool pressure also reduced. For delicate parts, it is very helpful, and improve deep hole drilling. Okay, so in this case, there is chances of getting higher length to diameter ratio. Uninterrupted drilling for small diameter holes. Conventional drilling necessitates a tool retraction, increasing machining time. But in this case, we are using ultrasonic machining, rotary ultrasonic machining, so we don't need any tool retracting unlike in your normal drilling operation. Small holes require more time as the machining rate decreases with penetration depth due to the difficulty in machining a continuous supply or new slurry at the tool face. So that is the case. That is common for both ultrasonic machining and rotary ultrasonic machining process. So in this case, rotary ultrasonic machining process, generally L by D ratio is very high. So minimum L by D ratio is achievable in this case is 2.5. Okay. So there are another applications by this ultrasonic machining process. So this is called ultrasonic sinking and contouring machine. Okay. So this is the first case when we get this ultrasonic sinking operation. Okay. So here ultrasonic vibration and we are giving some static feed to this tool. Okay. So now this is the shape of this tool. Okay. So we want to make same shape of this tool into the workpiece surface. So it is called actually ultrasonic sinking operation. Now this is the ultrasonic contouring operation. Here we are taking a very small tool. Okay, so this small tool, it is moved to this finishing, to this machining zone along the path to be machined. Okay, so you can move in a zigzag pattern or you can move in a helical pattern based on your requirement. So this is the small tool you are using here, very small tool. This small tool, it will move the workpiece surface and it will generate the contour. But in this case, actually, one single tool is used. Okay, so it's the shape of this tool is shape of the workpiece to be generated. And in this case, actually, small tool is used, and this tool actually moved along the profile to be machined on the workpiece surface. So this is the application here. So silicon nitride turbine blade sinking. This is the sinking operation. And after that, this B is the CFC acceleration lever and holes. So this is actually your contouring operation. It is done by using ultrasonic machining process. Okay, so another application is the production of EDM electrodes. Okay, so this ultrasonic machining process is used to produce the graphite EDM electrodes. Small machining forces permit the manufacture of fragile graphite EDM electrodes. Machining speeds in graphite ranges from 0.4 to 1.4 centimeter per minute, and RA ranges from 0.2 to 1.4 micron, so which is very good, and accuracy is achieved, it is plus minus 10 micron. So this kind of graphite electrodes can be machined by this ultrasonic machining process, which is used. So these graphite electrodes are used in electrode excision machining tool. Okay, so ultrasonic polishing. So ultrasonic machining process, the same concept can be used for polishing purpose also. So in this case, your amplitude of vibration is very less. Okay, so occurs by vibrating a brittle tool material such as graphite or glass into the workpiece at ultrasonic frequency and relatively low vibration of amplitude. So here amplitude of vibration, obviously it is very less. So fine abrasive particles in slurry appear the high spots on workpiece surface, removing 0.012 millimeter of material or less. Surface finish achieved, it is around 0.3 micron. Okay. So here you can see this is polished. So before polishing this one, and this is after polishing, you can see that by using this ultrasonic machining you can get a better polished surface also. Okay, so another application is the micro ultrasonic machining. Okay, so in this case your tool is very small. Okay, so it utilizes workpiece vibration, vibrating workpiece. Okay, so instead of giving vibration to this tool, here vibration is given to the workpiece itself. Okay, so vibrating workpiece allows inferior tool system design without considering transducer, horn. Okay, so micro holes of 5 micron diameter on quartz glass silicon made using tungsten carbide micro tools. So sintered diamond tool having high wear resistance used to machine multiple holes using a single tool. So can be used for machining 3D shapes also. Okay, so other applications are cutting of parts made of semiconductor at high removal rates compared to the conventional machining methods, engraving on glass as well as hardened steel and sintered carbide, parting and machining of precious stones including diamond. Now we shall discuss this material removal mechanism of ultrasonic machining process, how this material removal occurs and what is the rate of material removal during ultrasonic machining process. Okay, there are different kinds of models which are available in the literature. So various models are proposed by various researchers, and among these models, okay, so few very popular models which are Miller by Miller, he proposed in 1957. MC Shaw, he proposed in 1956, and also Kajan and Rosenberg, they proposed mechanical mechanism of cutting by ultrasonic machine process in 1965, and there are several other models are also available. So among these three models, we shall discuss about this MC Shaw's model, which is proposed in 1956. Okay, so the derivation of MC Shaw's model for metal removal mechanism by ultrasonic machine process. Okay, so there is few assumptions are there for this MC Shaw's model, who proposed in 1956. Here he assumed that these abrasive particles are spherical shape having diameter d and radius capital R. Okay, so these abrasive particles having spherical in shape having diameter small d or capital R, radius capital R. So although these abrasive particles are not spherical in shape, but for the simplicity of this MC Shaw's model, he proposed that these abrasive particles are spherical in shape. So volume of this particle chip from the workpiece surface is proportional to this 2R. So I shall discuss one by one from this figure. And this volume of material removed or particle chip from this workpiece is equal to the half of the volume of sphere of diameter equal to 2R. Here R is smaller. So here you can see this is the tool here, which is vibrating with the ultrasonic frequency, with the frequency of F and with the amplitude of A by 2. Now there are so many abrasive particles are there in between this tool and this workpiece. There are so many abrasive particles are there. So when some abrasive particle it is hit by the tool and it is impinging or penetrating into the workpiece surface here. So this is the diameter of this abrasive grain. So this is the diameter of this abrasive grit here, and this is the small d or 2R. Here R is the radius, capital R is the radius of the abrasive grain. Okay, so because of this impact force by this abrasive grit, it will impact into the workpiece surface and it will penetrate with an amount of h. H is the small h is the depth of penetration. So because of this penetration, it will make a spherical penetration into the hemispherical penetration into the workpiece surface. So this is the hemispherical penetration. We can assume that this is a hemispherical penetration with radius small r. Okay, so volume of material removed is because of this penetration. Okay, so volume of material removed is half of this, considering this hemispherical penetration. So this is the fracture volume. So here this is the fracture volume, and this one is the depth of penetration. How much this abrasive grain is penetrated into the workpiece surface. So now this zone is now exaggerated here with a bigger picture. Okay, so this is the abrasive grain. So this is the abrasive grain here. Okay, so this abrasive grain. Now this is the radius of this abrasive grain is capital R. Capital R, it is d by 2, small d by 2. Here h, this h is the depth of indentation into the workpiece surface, and this is the R here. Hemispherical, this much actually it is penetrated into the workpiece surface. So here this is the small r, which is the hemispherical zone which is removed or chipped off from the workpiece surface. And so obviously this one will be capital R minus h, and this is r by so d by 2, small capital R equal to d by 2. Now from this triangle, so we can consider this r minus h whole square plus small r whole square equal to this d by 2 whole square. Okay, so here note that 2r, small 2r equal to not equal to this small d. Okay, so small d equal to capital 2 capital R. Okay, so matter removal by throwing, there are two types of models are there. One is the throwing model, another one is the hammering model. Okay, so other methods of other mechanism of matter removal like cavitation, chemical action are neglected. So there is, because the slurries are there. Suppose we are slurry, it is a water based slurry. Suppose if you want to make machine on a glass, so this slurry can do the chemical reaction. So due to this chemical reaction, maybe there are some material removal rate, but here it is not considered. So material removal because of this chemical reaction and cavitation is not considered here. So only by throwing and hammering model it is considered. So radius of the sphere or crater formed due to this fracture is small r. Radius capital R in terms of this grid radius and the depth of penetration small h can be expressed as, okay. So from this triangle we can write this one, small r, this small r square equal to capital R square minus r minus h square. Okay. So after simplification we can write this one as capital R square minus r square plus 2rh minus a square. So here we can see that this abrasive particle size is it is in the micron size. So this depth of indentation h, which is penetrating, this abrasive particle penetrating into the workpiece surface, it is very less. Okay. So now we can consider, we can neglect this h square. So h is very small, so we can neglect the h square. So ultimately after simplification it will be 2rh, 2 capital R into h equal to r square. Now this volume of matter removed per grade per cycle, that is Vg here. So Vg already we have assumed that this is equal to the half of volume of material removed by the brittle fraction. Okay, considering small r as the radius. So this is half of this 4 by 3 pi r cube, the hemispherical zone, fractured zone. So this is the volume is 4 by 3 pi r cube. Now we have considered this half. So now we are putting this value of r. So here small r square equal to 2r into h. So small r equal to root over 2 capital R into h here. So now putting this value of r into this equation, so we can calculate the volume of matter removed per grain per cycle or per grid per cycle. Okay, so this is very simple here. So now here we can see 2 by 3 pi, and this one we can consider as K1. Okay, so this is the constant here, and 2 into capital R we can consider this one as the D. D is the diameter of this grid, and this is H as it is, we can put it here. So this is the volume of material removed, so it is millimeter cube per grid per cycle. Okay, so here K1 is the constant and H and D are in millimeter, are expressed in millimeter. So H is the depth of penetration and D is the diameter of this abrasive grid. Now we have to consider how many impacts are there per cycle. Okay, so now if we consider this is the tool here, so under this tool so many abrasive particles which is vibrating like this. So under this tool so many abrasive particles are there. Okay, so how many impacts are there by this abrasive particle into the workpiece surface because of one movement or one cycle of the tool into the towards the workpiece surface. So it is inversely proportional to the cross-sectional area of the grid. So now we can consider there are two examples are there here. Diameter of this abrasive particle is less, it is small d, and here diameter of this abrasive particle, this is d dash. Here this diameter of this abrasive particles are bigger size. Okay, so now this is the total, this one is the diameter of the tool. So under this tool here, as the abrasive particles grid size is diameter is small, so we can accommodate more number of abrasive particles, and here as the abrasive particle diameter is bigger in size, so under this tool we can accommodate only very less number of abrasive particles. So this number of impacts is obviously it is proportional to the cross sectional area of the abrasive grades. Okay, so cross sectional area is pi r square. Okay, so we can consider this one as d square. Okay, so it is proportional to the cross sectional area, proportional to the d square. Okay, so n number of impacts we can consider as the k2 by d square, considering k2 as a constant. So now the question is that is every grid is active. So active grid means just below the tool whatever abrasive particles are there, whether all the abrasive particles are taking part into the matter removal or not. It may happen that this one abrasive particle is hit by the tool, it again hits another abrasive particles, but it does not take part into the matter removal. So that abrasive particle is not an active abrasive particles. Also it may happen that this one abrasive particle it is hit by the tool. Okay, so it may actually move towards the away from the workpiece. Okay, so it may move away from the workpiece. Okay, so in that case also it is not taking part into the matter removal. So these active abrasive particles are those particles which are actively taking part into the matter removal. So we can consider a constant of proportionality, this K3, this probability that one abrasive particle is taking part into the matter removal, that can be considered as K3. Okay, so K3 is the probability that a grid under the tool is active and taking part into the matter removal. So volume of material removed per cycle. Okay, so it is K3 into volume of material removed per cycle per grid and number of impacts. Okay, so how many impacts are there? Okay, so here number of impacts are n here. Now we can put this K3, Vg already we have calculated, it is K1 SD 4 to the power 3 by 2 and number of impacts n equal to K2 by d square. Okay, so now K3, K1, K2 and K3 root over h cube by d. Okay, so this is the volume of material removed per cycle. Now we have to calculate volume of material removed per or volume of material removal rate per unit time. Okay, so if I have to calculate this per unit time, now we have to multiply this Vc with the frequency. So frequency means how many times this tool is vibrating in 1 second. So if we multiply this Vc, volume of material removed per cycle, multiplied by how many cycles are there, how many times it is vibrating in 1 second, then we can get the volume of material removal rate per unit time. Okay, so this is can be taken as MRRV. So here same as K1, K2 and K3 root over h cube by d multiplied by f. F is the frequency of vibration of this tool. So generally it is in the more than 20 kilohertz. So here we can get this one volume of material removal rate equal to millimeter cube per second. So this is equation 1 here. Okay, so volume of material removal rate per second. So F is the frequency of tool vibration. So now this unknown is that actually D we know here, D is the diameter of this abrasive grids, F is the frequency of vibration, that is machining parameter, and then H is the, here H is the depth of indentation. Okay, so H is the depth of indentation which is unknown. Okay, so now we have to calculate what is the depth of indentation at different machining conditions. So that's why there are two types of models are there. Okay, so MC Shaw he proposed two types of models. One is throwing model, another one is the hammering model. So now in next slide I shall discuss what is throwing model and what is hammering model. Okay, so there are two models out there. One is throwing model, another one is the hammering model. Suppose this is the tool here. Okay, so this is the tool. So it is vibrating with an ultrasonic frequency. Now there is an abrasive particles which it hits. Now this is the workpiece here. So this is the workpiece. Okay. Now this tool, it hits the abrasive particles. Now this abrasive particle is moved towards the workpiece surface, and it will impinge or impact into the workpiece surface, and it will generate this much of depth. So this depth is called the depth due to the throwing model. Here this distance between this tool and workpiece, okay, it is higher than, this distance is higher than the diameter of this abrasive particles. Okay, so this abrasive particle is hit by the tool. Now it will move through the slurry and it will penetrate into the workpiece surface. So this distance between tool and workpiece is more than the abrasive particles. So this is called the throwing model. So another model is, there is the tool here. So this is the abrasive particle here, and this is the workpiece. So okay, so this is the abrasive particle here. Okay, now this is the workpiece here. So in this case, this distance between this tool and this workpiece, distance between this tool and workpiece is less than the diameter of this abrasive particle. So it is less than this diameter of this abrasive particles. So here tool is in contact with the abrasive particles, and this abrasive particle is in contact with the workpiece surface. Okay. So here this distance between this tool and the workpiece surface, bottom surface of this tool and the top surface of this workpiece, okay, it is less than the diameter of this abrasive particles. So in this case, tool is every time it is in touch with the abrasive particles. So there are two models, one is throwing model and the one is the hammering model. So we shall discuss first throwing model, and again after that we shall discuss the hammering model. So grain throwing model. Okay, so a grain is thrown onto the workpiece surface by the tool. A tool displacement or vibration from the mean position at t equal to 0 at time t, assuming the sinusoidal vibration of this tool. So we are assuming this vibration of this tool as the sinusoidal. Okay, so at time t equal to 0, from this mean position to at time t, what is the tool displacement? So this displacement of this tool can be considered as this tool movement can be considered as the sinusoidal. So this displacement of this tool y can be considered as a by 2 sine 2 pi ft. So a by 2 is the amplitude here, and f is the frequency of vibration, and t is the time period. So velocity of this tool, so we can take the derivative dy dt. So it will be a by 2 into 2 pi ft, okay, into 2 pi f, and then cos 2 pi ft. So after simplification it will be pi f cos 2 pi ft. So what is the maximum velocity of this tool? So this maximum velocity when this cos 2 pi ft equal to 1. Okay, so then in that case this maximum velocity of this tool will be pi af. Okay, so this is the tool, it is, or abrasive particle, it is hit by the tool here, it is impacted into the workpiece surface. So this distance here more than this diameter of this abrasive particles. So at t equal to t is 0, and then after some time t it will hit the workpiece surface. So here one important assumption is that when this abrasive particle is hit by the tool, okay, it will gain the same velocity it will gain the same velocity as that of the tool. Okay, so this is the assumption we have considered here, assuming that the grit also leaves the tool at this maximum velocity y max. Okay, so now this sinusoidal profile or displacement is shown here. So this is the time period is t here. A by 2 is the amplitude of vibration. Okay, amplitude of tool vibration. Okay, now what is the kinetic energy of this abrasive particle it gains when it is hit by the tool? Okay, so this kinetic energy is, we know that it is half mv square. Okay, so here m is the mass of these abrasive particles. So this mass can be calculated as, mass of this abrasive particle can be calculated as pi by 6 dq. Okay, so d is the diameter of this abrasive particle, and rho a is the density of this abrasive particle. Okay, so now d, already we have calculated this v here. If we put this v here, so it will be pi square a square and f square. Okay, so this is the kinetic energy of this abrasive particle after being hit by the tool. So this is mass here, and this is the d square here. Now, one more assumption is that full kinetic energy of this absorbed by this workpiece before this particle comes to the rest. So when this abrasive particle is impinging or impacting into the workpiece, okay, into the workpiece, so this full kinetic energy of this kinetic energy gained by this abrasive particle, it is absorbed by the workpiece, and this abrasive particle, starting with a very high velocity, it will come to a rest position. Okay, so it will result in the penetration of STH into the workpiece surface. So this is the depth of penetration because of this throwing model. Okay, so it will penetrate equal amount of STH. So then the average work done. So if we consider as a triangular, so this one, if we consider as a triangular profile, okay, with F max equal to here, okay, so triangular variation of this force with the depth of indentation, if we consider, okay, so what is the work done by this abrasive particle before coming to the rest condition? Okay, so it will be half of F multiplied by this HTH. HTH is the depth of indentation, maximum depth of indentation. So assuming the triangular variation of the force F with the depth of penetration. So average contact stress acting on the workpiece surface, so it is equal to the brittle fracture of the hardness, or brittle fracture hardness of the workpiece surface. Okay, so average contact stress, so how much force is coming because of this penetration of this abrasive particle divided by the cross sectional area. So cross sectional area is the pi d into h. H is the here, HTS is the indentation depth. Okay, so now we know this pi r square equal to pi 2r into HTH equal to, we can consider this one as a pi HTH into d. So like this pi HTH has come. So it is a cross sectional area. So r square equal to 2rh, we already have calculated this one. Okay, so this one is pi STH into d. Okay, so this 2r equal to d, and this is STH here. Okay, so now this force, after simplification we shall get force equal to sigma multiplication of mdh th. Okay, so it is known that this kinetic energy particle is equal to the work done by this particle into the workpiece surface. So if we equate these two equations, okay, so this kinetic energy already we have calculated, this is the kinetic energy, and this is the work done by this particle here. Okay, so here work done is of F is already calculated from here. Okay, so F equal to pi HTH d, sigma equal to here brittle fracture hardness of this workpiece material, and then multiplied by this HTH. Okay, so this HTH here. So half, this same half is here. So now here we have considered sigma equal to this stress on this workpiece surface is equal to the brittle fracture hardness of this workpiece. Okay, so now after simplification we shall get the depth of indentation by the throwing model. It is equal to pi a f. F is the frequency of vibration, d is the diameter of this grid, then rho a Rho A is the density of this abrasive particle divided by 6 H. H, capital H is the hardness of this workpiece material, and it is root over. Okay. So now, if we know this hardness here, so we can put this hardness value into the earlier equation where we have calculated the volume of material removed. So this volume of material removed is K1, K2, K3 root over H cube by D. Okay. So this H cube, already we have calculated H cube here. So if we now put this value into this equation 1 for calculating volumetric material removal rate. Okay. So now we shall get in this form, this is the volumetric material removal rate in case of throwing model. So this value of HTH from equation 2 can be substituted in equation 1 for deriving the for evaluation of the volumetric material removal rate by the throwing model. In the same way, H can be derived if the material removal takes place due to the hammering action of this abrasive. Okay. So already we have calculated this throwing model, the depth of indentation. In the same way, you can calculate the depth of indentation by this hammering model. Okay. So this is the okay. So here this is the tool here. Tool at the top position here. Now it will come to the mean position. After that it will come to the bottom position. At this bottom position it will hit the abrasive particles because here gap is less than the gap between this tool and workpiece, top surface of the tool and the workpiece surface. Okay. So here from this top position it will come, this tool will come to the mean position, then it will come to the bottom position. When coming to this bottom position it will hit the abrasive planes. Okay. So gap between this tool and workpiece is less than diameter of this abrasive in case of throwing model, hammering model. So abrasive will partially penetrate into the tool. So here penetrating partially into the tool, and also it will partially penetrate into the workpiece here. So total depth of indentation here in case of hammering model, it is H subscript H equal to depth of indentation into the tool, which is HTH, okay, plus and depth of indentation into the workpiece, which is HWH. So it is a summation of this HTH because of this tool indentation, because of this indentation into the workpiece. So there are some assumptions are there in case of hammering model. So it is assumed that the grain is hammered into the workpiece. So gap between this bottom face of this tool and the top face of the workpiece is less than grid size of this abrasive particle. Mean speed of the tool is low in this case, and mean static feed applied to the tool, which is F, equal to the mean force of tool on the grid. Okay, so force acting on the abrasive particle only for a short time, del T. Okay, now you can see. So from this top position to the, it will come to the mean position. After that it will come to the bottom position. So while coming to this bottom position, it will touch at this point to the, this tool will touch in contact with the abrasive, and then abrasive is in contact with the workpiece. Okay. So at this point only there is a contact between this tool, abrasive and workpiece starts. So at this point only actually this force will start, force will increase. Okay, from a zero value for a time period of T, capital T, only this del T time actually it is in touch with the abrasive particle. This tool is in touch with the abrasive particle, and abrasive particle in touch with the workpiece, and as well as both, as well as with tool also. Now force will increase, then after that it will reduce to 0 for a delta time. Okay, so force F acts on the abrasive particle only for a short time, del T, during the cycle time T. During this time period del T, the abrasive particles is in contact with the tool and workpiece both. Okay, so del T, here del T is the duration of impact. So Fi max is the maximum value of this impact. So here also we are considering that sinusoidal vibration of this tool. So at this time, for this delta time, del T time, it is this tool is in contact with the both this abrasive particle is in contact with both the tool and the workpiece. So Fi max is the maximum value of the impact force. Fi force will vary with the depth of penetration by the grid, exposed contact area between the grain and the workpiece and the grain and the tool. And T, capital T, is the cycle time. Cycle time. Okay, so Fit is the force at any time, instantaneous time T here. So what will be the average force? Okay, because this force is varying at time for a delta time del T. Okay, so we can take the average value of this force by taking the integration from T, capital T, equal to 0 to T total time period. Okay, in this time period it varies from Fit to, okay, so Fit is the force at any instantaneous time T. Okay, so multiplied by dt. So it is averaged over this total time period 1 by T. So this will give the average force, okay, on the abrasive particle. Okay, so here you can see this is the tool here. So it is the C is the top position of this tool, and then O, it will come to the mean position of this tool, and after that it will come to this bottom position. So at this means it will touch the abrasive particle at point A, and after that this tool will come to this bottom position B. So this tool is in contact with the abrasive particle from A to B. So this from here to here it is time period T by 4, because this tool is coming, it will go to the mean position, then it will go to the bottom position, and then it will go to the mean position, it will go to the top position. So total this is the T cycle, cycle T, capital T. Here from O to A, B, it is time period, it is T by 4, and in between this A and B, it is in touch with the workpiece. This abrasive particle is in touch with the workpiece as well as with the tool. Okay, so this is the time period del T. This is the top position, mean position, this is the tool touches the grain at this point, and this is the bottom position. Okay, so from movement from A to B here is due to the impact on the abrasive particle. As the tool touches the abrasive, it experiences the resistance to move. So let us assume nature of variation of this force Fi is a triangular. So here also, like in throwing model also, we are considering this nature of vibration of this tool. We are considering as a triangular, although it is not a triangular. But for the simplicity of this calculation, we are considering this one as a triangular. Okay, so this is the total here to here, it is T by 4. Okay, cycle, half of the 1/4 of the cycle. At 1/4 of the cycle, only del by T time actually it is in touch. So here from 0 to, it will go to the maximum value, this force, okay, for this delta time del T. Okay. So again, so the abrasive will partially penetrate into the tool as well as into the workpiece. So total depth of penetration is equal to hammering model, indentation due to the into the tool, and indentation into the workpiece. So what is the mean velocity during the quarter cycle? T by 4. So from here to here it is the T by 4. What is the velocity here? At this point this tool is actually going half of, means it is going to the amplitude amount. Okay, so this is A by 2 amount, it is moving. So amplitude of vibration is A by 2 here. Okay. So what is the velocity here? Velocity we can calculate this A by 2 divided by T by 4. Okay, so this with this time T by 4 it is moving A by 2 amount of depth, means A by 2 amount of depth. Okay, so this is the velocity. After simplification we will get this 2A by T. So this is the mean velocity during the quarter cycle of the tool, mean velocity of the tool during the quarter cycle. So what is the time required to travel from A to B here? So time required, so from A to B actually it is moving this HS amount. HH is the total indentation depth due to the hammering model. Okay, So this H is by means total indentation depth divided by if we divide with the mean velocity of this tool, then we will get the del T amount. What is the time required for penetration of this full penetration okay, into the tool as well as into the workpiece. Okay. So from here we will get this del T. This value of del T here. Okay, so this force act on the grid by the tool starts increasing as soon as the grid gets in contact with the tool and workpiece at the same time. It attains maximum value and then it starts decreasing until it attains the zero value. So it from here to here its maximum value and then it will go to the zero value here. So movement of A to B is due to the impact on the abrasive particle as the tool touches the abrasive and it experiences more resistance here. So assuming the nature of vibration of the force Ft with time t as a triangular variation of this force Ft with the time t. Okay. So this integration of 0 to t Fi t dt, it will be expressed as Fi max is the maximum force by 2 into del t. So this is the Fi max here. So this is the Fi max here, okay, by 2 half, because we are considering this triangular area. So area of this triangle is Fi max by 2 into this del t here. Okay, so this is the integration we will give. Value of integration. So average force is 1 by t 0 to t Ft dt. Okay, so Ft dt we already got this Fi max by 2 into del t here. Okay, so it is 1 by t Fi max by 2 and del t already we have calculated in the earlier slide. It is Hs by A into T by 2 here. So from here after simplification we will get this Fi max. So this is the Fi max here. It can be represented with respect to the average force. So final expression of this Fi max is 4 into average force multiplied by A and then divided by St plus Hw. Okay, so it is Hs. St plus Hw is Hs, total indentation depth. Okay, so maximum force per grid is given by Fi max divided by N here. Okay, so maximum stress developed on the workpiece can be calculated as Fi max. So divided by N here. So this is the maximum force per grid and divided by the cross section area of that grid. So cross section area can be given as pi d h WH. Okay, so maximum stress developed in the tool also we can calculate. So this is the Fi max, again same Fi max divided by number of grids under the tool and divided by 1 by pi d HTH. So HTH is the depth of indentation into the tool here. So pi d HTH is the cross section area of the tool, cross section area of this abrasive into the tool here. Okay, so Fi max by N by pi d can be represented by, substituted by sigma W. So we can put it here as sigma W, then it will be SWS by STH. Okay, so here one more modification is that, so this STH by SWH by STH, okay, or STH by SW, this ratio of this, so this ratio of this throwing model divided by this hammering model can be represented as this sigma W by sigma T equal to, we can consider this one as A, J. So this STH by throwing model, indentation by throwing model by indentation by indentation by into the tool divided by indentation into the workpiece is equal to stress into the workpiece and maximum stress developed into the tool equal to J here. Okay. So now we have to calculate the maximum stress developed into the workpiece equal to Fi max by N divided by pi d h WH, okay, cross section area into the workpiece. Okay. So this Fi max by N, again we can put it here, put average A by HTH plus HWH, total indentation there. Then again this is the N, again see this N is here, and this cross section area into the workpiece. Okay. So now if we take this value, this common to this HWS as a common here, so it will be STS by SW plus 1 here. So STS by SW already we know this is the J, so this will be J plus 1, so that's why it will become, so this one will become J plus 1 here. Okay. So K2 is the constant of proportionality, it has come because of this N equal to K2 by D square. Okay, after simplification we will get this sigma W here. So stress W, sigma W can be replaced by Brinell hardness number H. So both are the same, sigma W equal to H here. So now this above equation can be simplified. So N we have considered here number of impacts. It is inversely proportional to the diameter of this d square of this abrasive particle. Okay, so it is the cross section area of this abrasive particle. Okay, so after simplification, this HWS will come in this form: root over 4 average A, amplitude of vibration, D is the diameter of this abrasive particle, by HW is the hardness of this workpiece material, then K2 is the constant of proportionality, and then J plus 1, J equal to STH by HWH. So STH is indentation into the tool, and SW is the indentation into the workpiece. Okay, so now if we substitute this value of this H indentation into the equation 1 for calculating material removal rate, we will get this final equation in this form: K1 plus K2 plus K3 for this third bracket, 4 F average into A by hardness of this workpiece material K2 into pi into J plus 1 whole to the power 3 by 4 and D to the power 1 by 4 into F. F is the frequency of vibration, D is the diameter of this abrasive grid here. So other things, everything we know here. Okay, so one thing I want to tell here. So although it is shown here this material removal rate is proportional to the 1 by 4. So theoretically, whatever we get material removal rate by using hammering model, okay, we don't get the same thing, same amount experimentally. So whatever these experimental results and these theoretical results, it does not matches well. So there are some simplification or modification. Mr. Shaw, MC Shaw, who has made some simplification there into his model, into his hammering model. Okay. Here this material removal rate is proportional to the D to the power 1 by 4 or D to the power 0.25. Okay, so that modification we shall discuss in the next slide. Okay, so from the theoretical calculation, it has been found that MRR by throwing model from the throwing mechanism is very less than this hammering mechanism. Okay, so material removal rate from this throwing mechanism is very less than the hammering model. Okay, so we can neglect that material removal rate from the throwing model. So discrepancy is observed between the experimental and theoretical results, and it has been explained by Shaw as follows. Okay, so actual shape of this grain, it is not a spherical. It is not a spherical. It is random in size. The abrasive particles are random in size. But we have considered this one as a spherical and smooth. So it is not at all spherical and smooth. So they have a projections of average diameter of this D1. Okay, so they have a projections average diameter of this D1, and this D1 is proportional to the D square. So D square, so this projection diameter is D1. It is proportional to the D square. D square is D is the diameter of this abrasive grain. Now if we take the square of this d1 square is proportional to the d to the power 4 here. Okay. So now this material removal rate is proportional to the d to the power 0.25. So from this hammering model here. Okay. So now this here. So now if we put this value MRV, volumetric material removal rate, is equal to, so d1. So if we put it here, d to the power 4 to the power 1 by 4 equal to, so it will become proportional to this d. Okay. So now if we increase the force by the tool, so MRV, material removal rate, will also increase. But in practice, beyond a certain value of this f, it starts decreasing. Okay. So if we increase the force beyond an optimum value, so this material removal rate, again it will decrease, because this abrasive grade will get crushed under the heavy load. So this abrasive grade will crushed under the heavy load. Okay. So now we shall discuss some problem. Okay. So based on this hammering and throwing model. So this based on this material removal mechanism, we shall discuss one problem here. Okay. So now I am reading that problem. Find out the approximate time required to machine a hole of diameter equal to 6 mm in a tungsten carbide plate of thickness equal to 1.5 times tungsten carbide plate, which has a fracture hardness of 6900 Newton per meter square, or it is equal to 6.9 into 10 to the power 9 Newton per meter square, and of thickness equal to 1.5 times of the hole of the diameter. Okay, means this thickness of this hole or thickness of this sheet is 1.5 times of the diameter of the hole. Okay, so now if it is diameter of this hole is 6, so now this thickness of this sheet will be 1.5 into 6 means 9 mm. The mean abrasive grain diameter is 0.015 mm. The feed force is equal to the 3.59. So this average force to the tool is 3.5 Newton. The amplitude of the oscillation is 25 micron here, and frequency is equal to the 25 kilohertz, and tool material is copper having the fracture hardness equal to the 1.5 into this 1000 Newton per meter square. The slurry contains 1 part of abrasive to 1 part of water. So means this C, value of C is equal to 1. And take the values of different constants. These three constants are there, K1, K2 and K3. Its values are given here. So K1 equal to 0.3, K2 equal to 1.8 and K3 equal to 0.6. Okay. And now this abrasive grain density is 3.8 gram per centimeter cube. Also calculate the ratio of this volume removed by the throwing mechanism to the volume removed by the hammering mechanism, or V, volume of material removed by throwing mechanism by volume of material removed by the hammering mechanism. And we have to calculate what is the time for machining of 6 mm diameter hole and 9 mm diameter on a 9 mm thick tungsten carbide plate. Okay, so now we shall see what are the informations are given here for the solution of this problem. So hole die is given 6 into 10 to the power 3 meter. So everything here now is converted into MK unit. Okay, so meter. So we have converted this length into meter. So this plate thickness is 1.5 times of hole diameter. So it is 9 into 10 to the power 3 meter here. Mean abrasive grain size is 1.5 into 10 to the power minus 5 abrasive grain size, and feed force is 3.5 Newton, and amplitude of tool oscillation A by 2 is 25 into 10 to the minus 6 meter. Frequency of oscillation is 25,000 CPS cycles per second. Okay, fracture hardness of this workpiece material is sigma W, or we can consider is SW, equal to 6.9 into 10 to the 9 Newton per meter square. Then fracture hardness of this tool material is 1.5 into 10 to the 9 Newton per meter square. Abrasive grain density is 3.8 into 10 to the power 3 kg per meter cube. And then this lambda, here lambda is written, or we can put this one as J. So J equal to this SW by ST equal to 4 by 6, 4.6 here. and K1, K2 and K3, this value is equal to 1, these values are known here. So there are different steps. The following procedure should be followed to solve the given problem. So what is the time required for machining the hole of 6 mm diameter? Okay. So now volume of metal removed, we know this equation 1. So this is equal to K1, K2 and K3 root over h cube by d. So here unknown is the h. So h we have to calculate first by hammering model as well as by throwing model. Okay, this step 1, this calculate the value of h, which is different for throwing model and hammering model. So after knowing the values of this h for throwing and hammering model, calculate the volume of metal removed by throwing model by this earlier equation and volume of metal removed by the hammering model by substituting these values of this h into the equation in the last equation. Okay. So now we can find out the total volume. So total volume is the VTH, volume of metal removed by throwing model, plus volume of metal removed by hammering model. So this total volume can be per unit time is Vs equal to VTH plus VWHL. Now calculate the total amount of material to be removed to make the required hole. Okay. So divide it total amount of material removed required to be removed by this Vs will give the time for making the hole. Okay. So this ratio is STS by SWHL. So after that we have to calculate the ratio, the indentation depth by the throwing model by indentation depth by the hammering model. So following are the steps for calculations. Okay, STS equal to pi f d, then root over rho a by 6 sigma w. Rho is the density of this abrasive particle, sigma w is the hardness of this workpiece material, a is the amplitude of vibration, f is the frequency of vibration, and d is the diameter of this abrasive particle. So all these values are known here. After putting all these values into this equation, we can get this STH equal to 1.78 into 10 to the power minus 5 millimeter. So now we have to calculate the penetration into the workpiece by the hammering model. So by hammering model it is 4 average, A amplitude of vibration is the diameter of this abrasive particle, sigma w is the hardness of this workpiece material, then K2 is the constant, lambda is the ratio by throwing model by indentation by throwing model by hammering model. Okay. So here we know all these values. After that we shall get this. We can get this one, this indentation by the hammering model here. So now calculate this. If we put these values into this equation, we can calculate the volume of metal removed by this both the models here. Okay. So here this is the volume of metal removed by this throwing model, and here volume of metal removed by the hammering model. So by putting all these values, H we know both the cases. Okay. So it will be W. So this is the WH. Okay. By this hammering model. Okay. So now step 3 is the time required to drill a hole equal to this volume of hole to be drilled. So volume of hole to be drilled is pi by 4. H is the diameter of this hole, and 9 is the depth of this hole. So total volume of metal removed equal to pi by 4 r square multiplied by this what is the depth or height of this holes to be thickness of this workpiece material, and divided by the volumetric metal equivalent, total volumetric metal equivalent by hammering model as well as plus throwing model. Okay. So it is coming as the time required is 19.289 minute. Okay. So now the second answer is that, answer to the second question is that volume of metal removed by throwing model by volume of metal removed by hammering model. Okay. So here by both the values, so it is coming as 0.023. So thus it is evident that the metal removed by this hammering model is much more than the metal removed by the throwing model. So approximately here 43 times. Hence for the approximate calculation V3H bottom volume of metal removed by the throwing model can be ignored as compared to the valuable matter removed by the Emery model. Okay, thank you.